Good evening, ladies and gentlemen. My name is Glenn Nagle from the CSIRO, Canberra Deep Space Communication Facility, where today we've been marking 50 years of NASA's Deep Space Network. Tonight you're going to enjoy a fantastic presentation by two leading figures of space exploration from NASA and the Jet Propulsion Labs. We're very honoured tonight to be able to be here at Questacon as it marks 25 years of doing great science. So we'd like to start our evening and invite to our stage the director of the Jet Propulsion Laboratory in Pasadena, California, and Dr Charles Elachi. Would you welcome Dr Charles Elachi?
Thank you very much. It's a great pleasure for me to be here in Canberra. I hope I pronounced it correctly. I usually say Canberra and I would get corrected. And I'm delighted particularly to see a lot of young people because these are going to be the explorers, of the future. 50 years ago, NASA started on a quest to explore our solar system. And from day one, Australia was a partner, with us in that exploration, particularly through the Deep Space Network, which is not very far from here. So basically all the data that we were getting from across the universe were coming through the station as well as the station in Madrid in California. So what I was going to do today is to give you a very quick overview of what we have learned in the last 50 years, and I'll try to compress it into about 20 minutes. But before I do that, I thought I would tell you, why do we explore? Because people always ask me the question, why do we explore? Why do we spend the money to explore that? So let me describe to you, at least in my way, why I think exploration is at the essence of what we do. Oh, sorry, push this. So somehow we believe today that about 13 billion years ago, there was a Big Bang. Now, I'm sure one of the young kids here is going to ask me what was before the Big Bang, so I'll tell you from now, I have no idea, what was before it. But somehow a Big Bang occurred and billions of particles, were generated. And then over billions of years, those particles got together and they formed stars and galaxies. And this is an example of 5 galaxies, which was taken with the Hubble telescope. And literally there are billions and billions of those galaxies in the universe. And if we zoom on one of those galaxies, that's what it looks like. And each galaxy literally has billions of stars, in that galaxy. And then if you zoom on some of these stars, we see that many of them, and now we're finding that almost all of them, actually have disks of dust, around the star. And those dust, agglomerate together, and they form small rocks, then big rocks, and then they form planets, like our solar system. So here you see our solar system, and here we are on this little blue dot, starting with Mercury, Venus, Earth, and then Mars. Then you move to the big planet, Jupiter, Saturn, Uranus, and Neptune, Uranus and Neptune. And then if you look at one of those planets, which turned out to be our planet, it had the right ingredient, the right temperature, the right chemistry, the right molecules, which have led to organic material and organic cells, which after a few billion years of evolution, basically led to the beautiful world that we sit in. So the key question is, how did that happen? How did it start from those particles, which were generated 13 billion years ago? And here you and I are sitting here having this conversation today. So what we are trying to do in NASA exploration of the universe is to write what I call the book, How Did That Happen? How did the universe start? How did stars form? How did galaxies form? How did planets form? And then how did life evolve? And is it common? Because if life is common across the universe, that will change our thinking of where we are. And if it's not common, it will change equally our thinking of where we are in this universe. And the question, are there planets like our planets? Are Earth-like planets all over the place? Are there many Westcom, across the universe? Are there many Canberras across the universe? So these are the kind of things that we are trying to understand by both sending robot and then sending a human to understand better of how did this universe, came about. So I'm going to give you now a very quick tour, of the solar system and tell you a little tidbits, about what we found out. So the first planet I'm not going to go through all the planets, that will take a long time. But Venus is the closest planet to Earth. So this is the second one from the sun, before the Earth. And it's about the same size as the Earth, almost exactly. It has an atmosphere, but something went wrong on Venus. It has a very thick atmosphere of carbon dioxide. So that became like what we call the greenhouse effect. So that's similar to where you have a greenhouse here, where you have a glass, and the light goes in, heats the inside, but then the heat cannot come out. And that's why it gets warmer inside the greenhouse, and plants kind of like it, except on Venus it went too far, you know, with the greenhouse. The same thing if you have your car parked in the sun and you close the windows, you know, when you come in and get inside the car, it's warmer inside than it's outside. Because the light goes in, heats, you know, the car, but it cannot come out. When Venus went rogue on us, you know, actually it was a lot of carbon dioxide, a lot of the light came in, heated the surface, couldn't come out, and now it's hotter than an oven. So it's really a very, very hot planet. But it has a lot of the geology which is similar to our planet. Actually, there are volcanoes on Venus. You have craters, we think there is some kind of tectonic activity going on Venus. So it's a model of our planet which went wrong. Let me go to the other side now, to Mars. Mars is also somewhat similar, you know, to Earth. It's about 1/4 the size. It has an atmosphere, but much thinner than our atmosphere. It's only about 1% of the atmosphere on Earth. But when you look at the detail, it has a lot of similarities. Here you look on the right is a Grand Canyon on Mars. On the left is the Grand Canyon in the western United States. If I didn't tell you that, you wouldn't have been able to tell what's the difference. Which one is from Earth, which one is from Mars. And this is more detailed picture. This is the Grand Canyon in the western US on the left. On the right, that's the wall of one of the craters, you know, on Mars that we were taking the picture from the rover. And what's interesting about this picture, you see those layers that you see in the wall of the canyon. That gets geologists very excited. Now, lots of things get geologists very excited, but when they see layers like this, they get very excited about it. And the reason is that the lower layers are older than the layer above it, because they were deposited first, then the next one get deposited, then the next one get deposited. So if you analyze the layers, basically you're going back in history of what happened at that location. The top layer will tell you about the last few million years, the layer below it will be a few million years before that. So what we are trying to do with our rovers is to go to areas where you see those layers and analyze each and every layer, and that will tell us what actually happened on Mars in the past. And that will give us an idea of how that planet actually evolved to where it is today. Earth has volcanoes, Mars has volcanoes. You know, on the right-hand side is what's called Mount Olympus. That's the largest volcano on Mars. It's twice the height of the Mount Everest. So this is a huge volcano, except it's extinct today. So it's not active. So sometime in the past, there were a lot of volcanic activity on Mars which created that volcano. But then it went, you know, dead after that. And one of the key questions, how did that happen? Why was there that change which have occurred? And this is a picture I usually give a test to my student at Caltech. I say, guess which one is Mars and which one is Death Valley in California. You can't tell the difference. Sometimes I even forget myself. I think the one on the right is the Mars picture. But the point I'm making is that the geologic activity on Mars are very similar to what's happening on our planet, you know, here on Earth. So one of the objectives of our quest of exploring Mars is to understand what was the situation in the past which led to the geology being very similar, and why is it different today? Today it's much colder than in the past, and could have life evolved, you know, on Mars. Now, let me give you an idea about the challenge to get to Mars before I tell you some of the results we have to do that. You know, when we launched from Cape Kennedy, and then after 450 million kilometers of travel, we had to land within 2-kilometer circle. To give you an idea about how challenging that is, that's the same if I go outside my office and hit a golf ball toward Canberra, and the golf ball has to go straight in the cup. That's how accurate we have to navigate that spacecraft. And to make it a little bit more challenging for a good golfer, the cup is moving, and you still have to get it straight in the cup. So that'll give you an idea about the technical challenges that we had to do this very accurate navigation, and why we were nervous, you know, when we were sitting at the mission operation. To give you another kind of challenge, the energy with which the capsule was arriving at Mars. We were coming in at 20,000 kilometers per hour. The amount of energy in that capsule was the equivalent of 18,000 race cars going at full speed. And within 7 minutes, we had to dissipate that energy and land softly on the surface. So later, at the end of my talk, I'll show you a short video I will transpose you to the mission operation room at JPL and show you a video of how actually we did that landing, and the challenge we were facing. So now we are on Mars, and this is one of the pictures that we thought was Curiosity, that the rover we have on it. And Curiosity is about the size of your car, medium-sized car. And it's basically a roving chemistry lab. It's the same chemistry equipment that you will find at the university. You have X-ray machine, like when you go to your doctor and they take X-ray picture of your teeth or your body, and that will tell us the composition of the material. It has what we call mass spectrometer, which also will tell us what are the composition. It has ovens, so we can take sample, put them in the oven, heat them, and see what comes out from the material. So the purpose of it was to be able to understand what's the chemistry on Mars, and are there organic materials similar to what we have on Earth. Now, when you look at a picture like this, for a geologist, they can learn a lot from just looking at that picture. This looks like a dry riverbed. It looks like an area where water existed in a lake, and then it evaporated, and you see these mud cracks that you see on the surface. So based on not only this picture, but many other data analysis we have done with Spirit and Opportunity, the one we sent 10 years ago, we believe that a few billion years ago, there were actually oceans on Mars similar to Earth. Mars was warmer, there were oceans on Mars. The water had no acidity in it, so you could have drunk it. If you were on Mars, you could pick the water and drink it. And then somehow that water has disappeared. And we have some theories why it happened. Mars is much smaller than Earth, so it could have cooled much faster than Earth. So the radioactivity which is inside the planet could have died earlier, and Mars could have cooled faster than Earth and became colder, and therefore the water got frozen and went below the surface. And we have indication that actually there is ice, water ice, below the surface. So we look at these kind of geologic feature, and then when you look at a little bit more detail, this is a picture from Earth from what we call a conglomerate. What conglomerate is, if you look at the bottom of a creek or a river, you see a lot of rounded rocks at the bottom, or pebbles. So if you take that water away and put dirt, and then put another river, and then more dirt, and compact it, it will look like this. It will look like all these pebbles with the mud which compact them. That's what we see on Mars. We see exactly the same thing. So we believe where we landed, actually a river was flowing in that location. It rounded those pebbles, like you see in the creek, river next to your home, and then it dried up. So we actually turned out, we landed in a riverbed. So the next step we did, we went and started drilling in the surface. And you see here a drill, and you see this gray material which came out. That got us all excited. As I said, geologists get excited for everything. And the reason it was very interesting is because Mars is red. And the reason Mars is red and called the red planet is because the surface is oxidized, which means there is rust, on the surface. Similar to the metal, if you leave it outside and it trays and you don't take care of it, it starts rusting. So that's what happened on Mars. Now, rust is not very good for organic material. That's why you take antioxidant. So we were concerned, how deep is that layer of rusting, on the surface of Mars? Because if it was too deep, we would have had to drill way deep to get to some fresh material and see if there is organic material in it. So the fact that as soon as we started drilling, we found the gray material coming out, got us all excited because that told us that the oxidation layer, or the rust, is very, very thin. And that very quickly we had access to very fresh, material. To make a long story short, we have done a lot of analysis of this material over the last year and a half. And basically the bottom line that every chemical element which is in your body actually exists on Mars. Oxygen, carbon, phosphorus, nitrogen, everything which forms the organic molecules which are in our body, actually we find them on Mars. Now, I want to be careful. We have not detected organic material, but we have detected the basic ingredient and the common ingredient which are common to organic materials. So the next question we're going to explore is, okay, if there was water on Mars, there were ocean, you have all the organic elements, the basic ingredient for generating organic element. Could have life started in the past? And if it did, what happened to it? And is there any signature of it? Are there any cells? Are there any fossils? Anything which exists on the surface of Mars? And that's what we're planning to do, and we're doing, as we are using that rover and future missions that we're planning. And that's where we're heading. So we have been on Mars now for about a year and a half. We have driven about 5 kilometers. Now that doesn't sound a lot, but it's a fair amount for a poor rover sitting on another planet. In fact, recently we celebrated that event that we drove a little bit more than 5 kilometers by having a 5K race at JPL. So we had all the employees going and running for 5 kilometers. Some of us took a lot longer than others, but that's where we're heading. These are the hills, that we're heading to. And the reason that's very interesting is you see all these layers that I was telling you about earlier. So we want to drive around some of these valleys and analyze these different layers, and that will tell us what is organic, if we detect organic material, what is the history of that area. And if there are any organic material, they tend to be preserved in what we call sedimentary rocks, which is what you see here with all these different layers. So that's what we're hoping to do over the next couple of years of our exploration. Now, let me move beyond Mars. Jupiter is the largest planet in our solar system. And you see the amazing dynamic which is happening on Jupiter. This hurricane is bigger than the size of our planet. And that's allowing us to learn a lot about the dynamics in the atmosphere, how hurricanes form, and so on, by monitoring these hurricanes. But there is one object which has particular interest, and that's a satellite of Jupiter called Europa. And that satellite is a little bit bigger than our moon. But the reason we find it interesting is it has ice on the surface. This is the whole satellite, and if you look at this area, and what you see is the cracks in the ice. This looks very much like when you fly over the North Pole. So that indication that actually the ice is floating on something, below it. And on top of that, we see all this orange stuff, which looks like organic material. We are not sure, but it looks like it. So the theory now is that Europa actually is a planet which has an ocean below the surface. You have this ice floating on the surface, and possibly organic material which is seeping from that ocean to the surface. So one of the next missions that NASA is planning to do is to start thinking, how do we explore such a planet? How thick is that ice? What is that organic material? Can we land on it ultimately in the future and penetrate down to that ocean and see if there is, life in that ocean? Because it looks like it has all the right ingredients. The fact that it has an ocean, which we know is made of water, because the ice on the surface we know from remote sensing that it's made of water. That means the temperature is comfortable. Otherwise, you wouldn't have a liquid ocean. And if you have water, and if you have organic material, then that's all the ingredient for life to potentially start. So that's one of the key potential, another satellite, which actually life could be on it. More recently, there was a new discovery which was made by looking with the with the Hubble telescope. We actually saw geysers coming out from the surface of Europa, which clearly indicate that there is heat, which is basically compressing that water and creating those geysers like Yellowstone or something equivalent here. So that created a lot of excitement in the science community in the US. So hopefully one of the young people here will be operating this mission 10 years from now or 15 years from now. Now let me move to the next planet, which is Saturn. Now Saturn looks very exciting, it looks very pretty, with all the rings which are around it. But in actuality, there is one additional interest from science point of view. You remember I told you earlier that we saw a lot of stars which have ring of dust around them, and the particles accumulate together, they form small rocks, and they form planets. Well, this ring around Saturn is made of dust. And the reason you see gaps in here is that the dust there have been swept and it formed small satellites. And if you don't believe me, here they are. So this is Saturn, which is way here. These are the rings, and these are satellites which are around Saturn. So in effect, we're seeing a mini solar system forming in front of us. And that's what allows us to learn how our solar system came to exist. And there are a couple of these satellites around Saturn which are particularly interesting. There is a satellite called Titan. Titan is bigger than our moon. It's one of the largest satellites in the solar system. It has an atmosphere the same thickness as our atmosphere. We see on it there is rain which occur on Titan. There are lakes, like you see in here, in more detail. And these are very large lakes. So they are like mini oceans. We see rivers on it, except all the water is frozen. So all of this rain, rivers, lakes is all made of hydrocarbon. So it's like the oil in your car. So here you have a planet which has the same feature as our planet, except it's all hydrocarbon. So I usually say, if you are on Titan, you don't have to go to a gas station. You just go to the nearest river and take a bucket and you can fill your car, with gasoline. On the other hand, if you light a match, the whole planet will blow up. So from science point of view, the reason this is particularly interesting is because hydrocarbon is organic material. So Titan could be what we call a prebiotic planet, meaning a planet which started forming. It has organic material, but because it's so cold, organic activity or life did not get started. So it was like frozen into a freezer, and you have all the organic material. So that's another target of exploration that NASA is thinking of going and exploring, because that will give us insight of what potentially our planet looked like very early in its formation, before actually life got started. Another satellite which is very interesting, which turned out to be very similar to Europa, is a satellite called Eneldus. Also, it's made all of ice. Now, it's a small satellite, and you see these cracks, you see on it, and when we flew over those cracks with a mission called Cassini, which is still in orbit around that, we found that they are warmer than the surrounding. And then when we look back, here you see geysers shooting out of that satellite, and these geysers are like 50 kilometers in height. So imagine you are standing in 50 kilometers up, you have this flow of ice which is shooting up into the sky, which also indicate that potentially there is an ocean below the surface on Enceladus. So that gives you an idea about the diversity that we have in our solar system. Now recently there was something very interesting which happened. As I mentioned, we have a spacecraft called Cassini, which is in orbit around Saturn. It went into a position where the spacecraft was just opposite the sun from Saturn. So Saturn was sitting in front of us, it blocked the sun from it, and that allowed us to see the very faint things which are around the sun. Similar to you walk in a room and there is a very bright light and you put your hand, to block the light so you can see the people which are around. And if you look carefully, you see this little teeny dot here. This little dot is us. This is Earth, as viewed from Saturn. So on this little dot is everybody you know, everybody you'd like to know, everybody you wish you never know, all your friends, or your people you don't like, all the people. All of us, we live on that little dot, in here. So that put in perspective where we are, even only in our solar system. Could you imagine if we were taking this picture from the neighboring star, doing it? So that gives a different perspective. And then Mr. Bolden will be telling you about his perspective when he was flying, in space, how we look, on this planet. Now, let me finish by one of the latest missions which have really done some dramatic event, and that's Voyager. Now, Voyager was launched 36 years ago, or 38 years ago now. And it has flown by all the large planets, and I showed you some of the pictures from that. But the key event which happened recently, it actually went beyond our solar system. So think of our solar system. You have the sun, you have all the planets around it, you have the wind being blowing out from the sun, and once it reaches the interstellar medium, that wind become like a shock wave, like in front of a car or in front of an airplane. Once you pass that shock wave, now you are into the interstellar medium. That means the medium which is influenced by the next star. So about 5-6 months ago, Voyager actually went through that shock wave and went into the interstellar medium. So this is, for the first time in the history of humanity, actually an object made by us, human, actually went beyond our solar system. And on that one, people, when we designed it, they kind of perceived this might happen. So they put a little disk, what we call the golden disk, and it was a message to if that spacecraft get captured by another civilization, how do you explain to them how we look like? What do we do? And I thought particularly you would be impressed that we had the Opera House as part of that, which is a description of the best things that our species, have done. And on that disk, there is an explanation of actually how do you play that disk? Because most likely that civilization will be very advanced. Most likely they will not be using disk. Many of the young people wouldn't even know what a disk is, in here. Because now they put it, a chip, in their computer and they get everything on it. So we had to explain to them, how do you play it, where we came from, what's the location, by looking at quasars in the sky. So it's a way of a message that we are giving to the next civilization that might capture that spacecraft, what we are all about. And let me finish here before I show you the video. All of this is possible because of stations like the Tidbinbilla station. And that's where Australia plays such a major role, as we receive all that signal, came down to Earth, through those stations. So now what I'm going to do is to show you a few-minute video. I'm going to transpose you to JPL in the mission operation room the night we landed, our Curiosity. And to give you an idea, as it was landing, there were 50 million Americans which are looking at our website or were at the museums, watching what's happening. And the following day, there was 1.6 billion hit on our website from all around the world. Now, some of them were me checking every 5 minutes, or Charlie checking every 5 minutes to see what was going on. But still, it was an amazing thing. And the other thing I'd like you to watch, look at the people which were actually operating those missions. They're not much older than some of the people who are sitting in here, and the diversity of those people. So hopefully, a few years from now, some of you who are sitting in this room will be the people operating the next mission that we're flying, so we can play.
Things are looking good. Coming up on entry. Vehicle reports entry interface. At this time, it will begin pressurizing the propulsion system to increase the thrust of the system. We'll use that for all the maneuvering in the atmosphere we're about to do. We are standing by for guided start of guided entry. We are beginning to feel the atmosphere as we go in here. The vehicle has just reported via tones that it has started guided entry. At this time, the vehicle is beginning to steer its way to the target. We have seen peak deceleration. It is starting its first bank reversal. It is reporting that we are seeing G's on the order of 11 to 12 Earth G's. Bank reversal 2 is starting. We are now getting telemetry from Odyssey. We should have parachute deploy around Mach 1.7. The parachute is deployed. We are decelerating. Heat shield has separated where we found the ground. We're down to 90 meters per second at an altitude of 6.5 kilometers and descending. Standing by for backshell separation. We are in powered flight. We're at altitude of 1 kilometer descending. Standing by for sky crane. Sky crane is started.
Signal to us, you remain strong.
Touchdown confirmed. We're safe on Mars. Curiosity will take us.
Got thumbnails.
Today, right now, the wheels of curiosity have begun to blaze the trail for human footprints on Mars. This is an amazing achievement.
Well, today on Mars, history was made on Earth. The successful landing of Curiosity marks what is really an unprecedented technological tour de force. It will stand as an American point of pride far into the future.
Well, tonight was a great drama that was played. I could only think of the words of Teddy Roosevelt as I was sitting there. It is far better to dare mighty things even though we might fail, than to stay in the twilight that knows neither victory nor defeat. Now, this showed you what was happening, in Pasadena at JPL, but also similar thing was happening at the station here in Canberra. It was full of audience who were sitting there, and including government official and American ambassador. And just a little anecdote to take with you, because it just happened Mars was over Australia at that time. So the signal came here first before it went, to JPL. So you knew about what's going on fraction of a second before we knew what was going on in that area. So that shows that Australia was at the forefront, of exploration.